Welcome to the fifth presentation in the fifth webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube and Bilibili. This is the fifth webinar of our fifth series, which we will continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the fifth series will be distributed through the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Dr. Andreas Seidel-Morgenstern at the Max Planck Institute for Dynamics of Complex Technical Systems in Magdeburg, Germany. I'm Nicholas Wilkins at Svante Technologies Incorporated in Canada. Today's webinar will be moderated by Giuseppe Pizzella at King Abdullah University of Science and Technology in Saudi Arabia. We're required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you have not already. Our dues are minimal, only $20 per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants, and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @adsots for future updates regarding IAS events, webinars, and information about scientific meetings. Please help us expand our YouTube channel by liking this video and subscribing. I'll now hand it over to Giuseppe, who will moderate the YouTube Q&A.
Hello, everybody. It's my pleasure to welcome Dr. Andreas Seidel-Morgenstern to today's webinar session. Dr. Andreas Seidel-Morgenstern received a diploma in chemical engineering at Magdeburg in 1982 and a PhD at the Institute of Physical Chemistry of the Academy of Science, Berlin East, in 1987. Between 1991 and 1992, he was a postdoc at the University of Tennessee in Knoxville. Afterwards, he completed a habilitation at TU Berlin and worked for the pharmaceutical company Schering. Between 1995 and 2022, he was the chair of the chemical process engineering at the University of Magdeburg. Since 2002, he has been the director at the Max Planck Institute for Dynamics of Complex Technical Systems. He has published more than 500 papers addressing different areas, including heterogeneous and homogeneous catalysis, crystallization, adsorption, and preparative chromatography. He has also served as the president of the International Adsorption Society between 2019 to 2022. He is a member of the Berlin-Brandenburg Academy of Science and the US National Academy of Engineering. During the webinar, questions can be submitted to the speaker as comments on the YouTube live stream. Questions will be answered at the end of the presentation. With that, I welcome Dr. Seidel-Morgenstern again and pass over the presentation to them. Thank you.
So thank you very much, Nick and Giuseppe. I just try to come into the system. Can you see my slides and maybe my face on the webcam?
Yep, everything looks great.
Okay, and the sound is nice as well. Okay,
exactly.
Then very good. Then I would like to start. It's really a big pleasure to give this webinar on dynamic methods to measure competitive adsorption isotherms. I see it a little bit as a continuation of a webinar which I gave now 4 years ago, more than 4 years ago, in the first series of this webinars. And I'm very happy and glad that this continues and is sustainable and fruitful. So in the last webinar, I have shown this first slide where we see the big area adsorption technology is involved in. We need materials, we need to understand them in terms of thermodynamic properties, kinetics, and we want to do processes. Huh? So today I will focus again on the middle part, so the connection between thermodynamics and dynamic responses that we can record. So let me see now this. Yeah. There are so many methods to measure adsorption isotherms. That's maybe for beginners always a bit confusing. In this forest of options recently, David Scholl, Krista Walton and colleagues published a quite nice paper. You might have a look in that. 18 methods were described and compared under different viewpoints. So my view is always to look if the methods are static or dynamic. That means if they need the time information inside or if they really just look at equilibrium data. Today I will focus on dynamic methods. So we observe something over time, which is then also influenced by kinetics of the process, but we are interested in getting thermodynamic data, the single component isotherms or the degree of competition. In this area, we have a couple of options. We need, of course, very well-defined experiments. So the input information must be clearly defined, the procedures must be defined, and then we can expect even from time-dependent information to get out thermodynamic data. This is often done for single components. It's less done for mixtures, although the problem we all face sits in the mixture separation side. So today I have splitted this webinar into 3 parts. They differ more or less by a small parameter that we can vary in the experiments. We will in all cases use fixed bands or columns or chromatographic columns, and we will manipulate the input and record the output. And we can distinguish between situations where we really create a total breakthrough. That means we have a step input change at the inlet, and we keep this sufficiently long until this system, the adsorber, is equilibrated. The opposite is to use very small perturbations, small pulses on different levels of different initial conditions, and we work then with very small feeding times. And there is obviously an intermediate scenario possible where we have no pulses, but also do not reach the complete breakthrough. All these 3 variants of manipulating the inlet of an adsorber lead to possibilities to extract the equilibrium information. That's my goal for today. Let's start with part 1. This is probably the most familiar to you. Breakthrough curves are all around. I have shown here an example on the left where 2 components, red and blue, in different feed compositions break through. They might be influenced by kinetics. Then we have these more sigmoidal shapes, or they can be belong to very efficient systems, as the chromatography community calls it, and we have very steep responses. So the question is, how can we get from such an observation the thermodynamic information we are interested? So that gives me the chance to refer for the first time. I will do it later again to Nick Wilkins, our chair of today, and together with Arvind and Farouk, they published recently a very nice paper related to many aspects of measuring and interpreting column breakthrough experiments. For adsorption, equilibrium, data extraction, but they address also the other aspect, the kinetics, because breakthrough curves provide access to both types of information. I will today exclusively focus on the equilibrium part of that. So breakthrough curve examples are shown here. Just it's a arbitrary collection. I just want to say we have for single component systems, maybe this series of overloading in all cases where the concentration was changed, increased. We have a drastic change in the breakthrough times. We see a shock formation on one side and a dispersed front on the other side. Quite a typical information. The binary example below shows the situation that the final equilibrium state is not directly accessed from the initial condition, which is here a non-preloaded column, but we see rather an overshoot of the first eluting component. So there are situations where we have a higher concentration in the outlet than in the inlet. These overshoots are very typical in breakthrough experiments. And the last slide here shows a situation for 3 components where the dissolved branch is also visible. What you see here is the detector response as a UV trace where we can see the intermediate plateaus, 3 shock fronts, and at different position, again, plateaus forming in the desorption side. These are all interesting informations. And as I will explain, they all are strongly influenced by the thermodynamics and thus provide us the possibility to solve inverse problems and to extract loadings or thermodynamic data from such observations. The key to understand how this works is, of course, the mass balance of such a fixed bed. And I have given you here the classical dispersion model, which many of you know very well, where all kinetic effects, for the sake of simplicity, are captured by this apparent dispersion coefficient, which in the chromatography community is expressed very often as the latent number of the column 1. There is a clear connection between the two. By matching the second moments, we can derive this equation. Yeah, in this mass balance, we see a phase F with the function of the porosity fluid phase fraction. We see there's a convection expressed by U here, and we have this equation that should be conserved and should drive for the breakthrough experiments the system from the initial state to the feed state. Equilibrium theory is now a very powerful tool to extract the key features of such response curves by assuming a permanent equilibrium between the load and the fluid phase concentration and neglecting the dispersion totally or all kinetic effects which are lumped in this apparent dispersion coefficient. Then this equation, under the additional assumption that the velocity is taken constant, I will come back to this matter later, forms a very classical hyperbolic first-order partial differential equation for which a very strong theory, a mathematical theory, is available. I refer to these 2 books by Elris and Amundsen and give in the end a few more references. So this equilibrium theory now allows us, exemplified here, for a single component system, where this stands for the single component isotherm, can be this equation can be rearranged for the single component isotherm. The result of the isotherm now becomes a very important parameter because the 2 phases are in equilibrium, they are connected where there's load. And we can predict, for example, for a given concentration, indicated here by the asterisk, the time when a front will leave the adsorber of length L. So the speed of this front is then determined by the slope of the adsorption isotherm. This time t0 here is capturing the velocity. It stands for the dead time where also the size of the column shows up and the volumetric flow rate. So all these are very classical equations you find in many textbooks, but they form for today the platform to expand. Let me illustrate it a little bit more by showing you now again for a single component system and a nonlinear isotherm of the Langmuir type, where we have this kind of curvature, that this theory explains us that there are two types of propagations developing. One type is a shock formation, where instead of the slope, a difference in loadings and concentrations drives the speed of the front. This is related to the slope of these operating lines here. And we have the wave shape, which is here for the Langmuirian systems, characterizing the desorption branch, where then the slope of the isotherm shows up. So this explains the self-sharpening effect of Langmuirian systems, where adsorption is favorable because we have a sharp front, but we pay the price in the desorption, which follows then wave expressions, and we have dispersed responses. This can change for anti-Langmuirian isotherms, where the adsorption will be dispersed, the adsorption front, and the desorption sharpened. Of course, there are more complicated cases which I will not address today, when the isotherm has an inflection point that we surpass by the feed concentration. Then composite waves will form, which are also accessible or can be treated by the theory. The binary system theory gives us also direct access to the operating concentrations that you saw in the earlier example. So if we assume that the classical Langmuir equations for two components, parameters given, they are chosen in a way that the saturation capacity is different, and even a crossing of the isotherms is possible. And for fixing the feed concentration of the first component, we can play with the second feed concentration in blue, here from a value of 1, decreased by a factor of 10. Everything else is constant. So this has a tremendous effect on the shape of the elution profiles, on the degree of overshooting, and on the difference of the two characteristic retention times that show up, which are very close here, but there is a big overshoot, and the situation has changed, and everything depends on the feed concentration. There's a solution for that construction possible, which I'm not going to explain today. I did this in the old webinar of 2002. It allows us very easily, when the isotherms are known, to predict the retention times and this plateau concentration. The latter one is the solution of a quadratic equation. We will come to this order of polynomials in a minute later. So let me come to a case that I will treat today a bit more extensively and will illustrate it by an experimental example. This is breakthrough behavior for 3 components. If we have 3 components and we have Langmuirian systems, this mentioned theory is also capable to predict the total analytical description of the situation. So let's first look at the competitive Langmuir equation. The notation that I use is that the saturation capacity QSI is here. We can combine the 2 coefficients with the B into the Henry constant. We can also express, and that's the formulation which I will use to make the Langmuir isotherm, by having the Henry constant as one parameter and the saturation capacities as the second. Probably most of you know that there is a thermodynamic requirement, maybe Broughton discussed it most extensively, that consistency is only given if all these saturation factors are the same. And these simplifies. In the upper case, you have 6 free parameters, in the lower case, only 4. I will also touch this in a few minutes again. So solving the material balance, the dispersion model that you saw before for these three components, for certain feed concentrations, which are given here in this example, the blue concentration is the lowest, then comes the red one, and then comes the highest concentration, which I have not indicated. We generate some trace-through behavior, where the first eluting component, in this case the blue one, has a characteristic overshoot. Then it goes in a second intermediate plateau before it reaches the final equilibrium state belonging to the feed. The second component elutes only after the first shock time, after the first transition, and undergoes then a transition into another intermediate plateau before settling down in the feed state. Whereas the strongest bound component directly enters the feed state. So these characteristics, them here, also three of them. 2 for the blue component in plateau 1 is a characteristic value for blue, and in plateau 2 as well. And the red plateau value in plateau 2, these 6 informations characterize now the system. And so if we have experimental evidence, we can go back to the isotherm. How can this be done? For this, I need to give you a very brief, overloaded slide of the mathematical details. So for those of you that are interested in that, you should read the classical papers, in particular Ayers and Amundsen solve these problems in a very elegant way. The analytical solution of these experiments that you see here on the top proceed or can be derived using a transformation of coordinates. So the concentrations we saw over time can be transformed in a so-called omega space, where we also have the transitions from a feed state, from an initial state, in a first plateau state, in a second plateau state into the feed. But this omega space is constructed in a way that all transitions are orthogonal to each other. That means in one transition, only one of the omega values changes. This elegant transformation, which is shown here in the blue framed equation, allows us to derive this analytical solution, which you see in the bottom. So the key is to solve this transformed equation for the feed state, assuming that the initial state is a not preloaded column or a fully regenerated adsorber, as you can call it, then the initial omega values are always the initial slopes of the isotherms. But the feed state is the interesting one, how you perturb your system, how you design your experiment with which feed mixture. And so then you need, for a 3-component system, to solve this polynomial equation. This is a polynomial in omega of the order n. And for 3 components, the equation is like this. We have a cubic equation that provides 3 omega values corresponding to the feed state. This is essentially everything you need to proceed and to complete the whole construction, solving this cubic equation. Then you can calculate retention time, which that you all know. The equation is a very general way written, where you can have even more than 3 components in the system, because the solution provided the isotherm type, the Langmuir isotherms also for the other components. You can derive all these transition shock front times, and here are the corresponding plateau concentrations in a very general way. So this is a very beautiful, very elegant analysis, which I exemplify below in the button for n equal to 3, for our case of the ternary system, where we have 6 characteristic informations that we need to construct the analytical solution. So we have these 3 retention times, which now just use the omegas of the feed and the initial state. The initial state value are just see the 3 omegas corresponding to the state. That means the 3 roots of this cubic equation. And you have the same for the plateau concentration. Make go down 0, but 3 of them that I explained before result from this equation, and we have analytical solutions again where we have the chance to calculate the plateau states. So this is beautiful, and I just want to say that we can extend that to more than 3 components. I do it in the button, but for those of you that very often have maybe binary data, of course, there is a reducing of this theory possible to the binary case, where we have solved quadratic equations, and we have 2 attention times originating from the same formula, and just as one I did it before.
Andreas, are you able to hear me?
I hear you, yeah.
Would you mind turning off?
Would you mind turning off?
There is a bit of a lag with the audio. I think it might be taking too much to buffer over the internet connection.
So what do you want to ask me, Nick? I should go back?
You can continue from where you are. It's just the audio quality has been suffering a little. I think it might help if you turn off your camera. It won't have to send as much information.
I can do that, sure.
Okay.
Let me just a second. I need to go to the Zoom again. I stopped share screening for a moment, and I stop the camera and share again. Let me know, Nick, if it's better or not.
Right now it sounds better. So yeah, we'll just have you, and if you want to bring up your laser pointer again.
I lost it. It's here. So I try again now without the camera. I hope you can hear me better. So it's okay?
Yep, it's already sounding a little better. So thank you.
Okay, then let's try like this. No? So I was summarizing the results of the analytical solution of equilibrium theory based on the omega transformation. All this will be needed to understand how we analyze the data later. I have shown on top for 2 components. Maybe interesting, this is the last remark here. If we would have n components, more than 3, for example, then there is a clear formula, or we can clearly understand how much information sits in such experiments when we have not preloaded column. So 1 information is in a single component experiment. 3 we have here in the binary case that you just see on the slide. We had this 6 information on the previous slide, and always we add another front and more plateaus. And this formula here shows you how this would develop if you would be able to record also for multi-component system the information. Okay, let's come to the next step, understanding how these things are connected, how we can exploit them to measure isotherms. So the ternary system that I introduced before, you see on the left again, on the bottom, but now I perturbed it by kinetic effects, but the general features are captured. What can we see now here? Where is the capacity, the isotherm information we are interested? Of course, we need to integrate now because we have a retention. So the feed is immediately switched from initial state to feed state, but the outlet responds in this retarded way, and everything what we do not see immediately must sit in the column. But if we have reached the feed state again in the end, then the column is equilibrated again at the feed state. But we have characteristic intermediate states. So we can do various integrations of the outlet signal compared to a characteristic information. And so we have here the integration formulas. And when we interpret the integral, the retained effect is partly due to changing the fluid phase concentration and partly due to changing the solid phase concentration. The phase ratio will be needed. And so here we have amounts stored in the column. You see this by having an integral going from the initial state to the very end, to the feed state. Here you see the blue curve under kinetic influences even, and we have to subtract everything belonging to the overshoot. So the overall area, this integral, is the part below the characteristic feed state, and plus minus this one. If you look for the red component that goes in a different trajectory to the feed state, also there is some things that need to be subtracted, and the green curve not. Seeing now at these areas, we have the different capacities of the three components belonging to the feed state. So these are real ternary equilibrium data. But we can also extract information, for example, for the first component, a single component isotherm point, provided we can measure, we can see this first plateau concentration, which is clearly there in the equilibrium theory. In experiments, we might lose it for not sufficiently fast kinetics. Here is a case where we still see it, and if you can identify this, you can do this integral. Then the reference line in your integration is now this plateau concentration, and everything in this area is now a single component isotherm point belonging to this plateau concentration of the first component. You can do this for the second plateau. If you see for the blue component the second plateau concentration, which would be this one here, you can now take this as a reference line for integration. Everything below is positive, and you have to subtract this area. So my minus is a little bit shifted. And you can do for the red component the same. So the two lower cases are now binary equilibrium data, binary equilibrium isotherm points. This is a single component point, and here we have three ternary points. All can be analyzed in the same way and are a result of an integration. All this comes from this single breakthrough experiment. So 6 equilibrium data can be extracted, provided the plateaus are visible. But 3 we always can extract because we know the feed state. We don't need to measure it. Let me illustrate this on an experimental example. So we did an analysis in a liquid system. We work with chromatography. There is octadecile silica, a good stationary phase, the reversed phase material C18, small particles, small adsorber, small column, mixed solvent, which we see as an inert solvent in a way, and we fix the flow rate and the temperature. The 3 components I show you are these aromatic components, simple phenol and some phenyl ethanol, phenyl propanol. And we studied typically, and this is an information I will come back in the summary, very often it's good to have additional pulse experiments in the beginning to characterize your system. One information you need is the phase ratio. And you can get this by pulse responses to non-retained components. Here, uracil is known to be a good T0 marker, a dead volume marker that gives access to this. Then we have here additional information about the separability of these 3 components just by analytical small pulses. You see there's phenyl propanol, the PP is strongest bound, and the phenol elutes fastest. We can take from these pulse times, knowing the T0 and the F, the Henry constants immediately. So we have an initial very good estimate for the Henry constants. And these preliminary experiments also give a quick estimate of the plate numbers just from classical formulas which assume these peaks are more or less Gaussians. So from the width at half height and the retention time of the maximum, you can estimate the plate number, which is roughly 300 in the average for this system. Yeah, I wrote here extra column dead volume subtracted. I will not go too much in experimental details, but of course you have typically also outside the column some dead volume effects, and by estimating them and shifting the time axes, we can get rid of them. This is often an important issue in pulse experiments, but also during breakthrough experiments, where sometimes the step input comes from a different origin than the origin of pulse inputs due to experimental reasons. So here is an example of such a breakthrough experiment for the three components. You see the three feed concentrations, roughly 1, 2, 3. So we have an increase from blue to red to green. Sorry, I had a phone call. So, and we see here the recorded responses. These responses were recorded by taking fractions at the outlet and reanalyzing them with rather accurate HPLC. And we see clearly the figures, the features that we indicated before. So 3 characteristic times and 3 characteristic intermediate plateaus. The first one is not too easy and not fully developed, but it can be estimated quite well. So this gives us the chance to do these 6 types of integrations that I described to you. In this particular case, we also can do a very quick estimation of the retention time. So the first time is roughly 13 minutes. We can do maybe more precisely. The second is about 16 minutes, and this is a little bit more than 20 minutes. So if you have a chance to estimate these times quickly, that substitutes the calculation of the integral, because the times and the integral are easily directly connected. So you can sometimes save the integration if you see the times very well. Less frequently, more often, I would say, you have problems seeing the plateaus. If you have the times, you can also calculate without integration with the plateaus directly the loading points belonging to the 6 scenarios. The single component point for the first plateau concentration, the 2 binary points, and the 3 ternary points, which are connected with this last retention time. Now, these are useful analytical expressions. Let me show you what comes out with this experiment. So knowing the F and the T0, having these 3 feed concentrations, and just analyzing the loading, the feed state, we have these 3 ternary equilibrium data. Now, since we can estimate quite well the plateaus, you see the 30.4 is above the feed state, the other one is a little bit lower, and 69.9 exceeds the 50 in the feed state for the second component. And so this information now comes in addition and provides these 3 other points. So far we have just analyzed, integrated the breakthrough curves. No isotherm assumption. We have just generated loadings which belong to this feed state under equilibrium conditions. Now we can proceed by assuming an isotherm model and have for this loadings a theory. If we assume the Langmuir model for 3 components and leave the saturation capacities free, independent for each component, we end up to 6 parameters. If we take the consistency assumption into mind, then we reduce this to 4 parameters because the 3 saturation capacities are the same. In this objective function, this is captured. It also has a weight. The weight can be 0 in case certain information is not available or not visible. Imagine you cannot see these plateaus very well. So now I have a totally overloaded table, and I will not go too much in detail. It shows again on top the experimental input information, and then results for a second experiment where we did the same exercise. In the second experiment, you see on the top, the red component was less in the feed. So the 50 was reduced roughly by a factor of 3. And we could again do the exercise. And now we can estimate with the objective function that you saw before, the 3 Henry constants, the 3 saturation capacities. We can do various scenarios, taking the Henry constants from independent measurements. Here you see the 3 initial slopes taken from the pulses, which of course reduces the number of free parameters to 3, or even to 1 if we assume the same saturation loading is there. So the most simple case is we just estimate 1 single saturation capacity, taking the Henry constant here. And we can also combine 2 experiments if you have them. So this will be, I mentioned, publication is submitted with these details. For us, it was quite interesting to run these scenarios and to see here the 3 Henry constants of the green component, of the red and blue, very small. You see also the value taken from the independent measurements, and the fluctuation is not too big, so we can estimate this quite well, if not that we assume it. Stronger deviations are in the 3 saturation capacities for the first one, for the second and the third. But this is also a little bit far away extrapolation. So in the core of the parameter information basis, they don't differ too much, as I show you here, where only the results from experiment 1 are shown, and we see the 3 isotherms as predicted for the different sets of parameters. So we see the differences come not only from experiments, the integration brings an issue, also how we interpret the results and how we run an estimation procedure influences. So these are differences which are, of course, very high if you want to design precisely an adsorber, but altogether they are not too bad. By the way, the points here are independent breakthrough experiments from single components, which we did for validation and which I will not comment too much. The validation which was most satisfying for us was to do 2 more experiments 3 and 4. You see in experiment 4, the middle component is now in huge excess. And this, together with the experimental points, we just see here the curves coming from parameter set 6 before, and others are quite similar to this. So the agreement of predicting now other scenarios is very high. This goes even to the prediction of the desorption branch, which I did not discuss before. So our paper is under review currently. We hope it will be accepted, and then there is access to this information. So I will soon stop this part with the breakthrough curve. Just want to mention there are more scenarios, interesting scenarios. For example, you can work with preloaded columns. Here is the same ternary system in a theory where we have now 3 initial values which are not 0, and we go to a new equilibrium state. And we see here also the desorption part and interesting plateaus. So the theory, the equilibrium theory explains in detail the course of this, and similar integration strategies could be used. So you can do also staircase experiment. This is maybe a first breakthrough experiment for a binary system. And once you are in equilibrium, you increase the concentration of the 2. So in this way, you might automate experiments a bit better. Here is an example of anti-Langmuirian cases where similar integration strategies can be applied, most simply for the desorption branch. But you can also analyze the dispersed waves in any case, and I will come back to this in part C. Yeah, before closing this, I want to come back to the flow rate, because we like to work at the moment with liquids where the velocity U is a constant. You remember I took it out of this differential. In the general way, we have to use chain rule, and we have to have an understanding how the flow rate changes over space, and in this differential equation then over time. So in the liquid phase, this is just a factor, the flow rate, or here expressed as the volumetric as the volumetric flow rate, not as the velocity. And the integral takes advantage that this is a constant. So Nick and Arvind in their paper addressing the gas phase area point clearly out that also the flow rate Q of T needs to be measured, because you need the product of flow rate and concentration. They use this Y symbol here. Now you can normalize this. This is more or less the Y-axis of a breakthrough experiment. And then you can do similar integrations, also for the gas phase. But you need to know how the flow rate changes. Otherwise, you cannot close the mass balance. So this is a slide where I can take a gulp of water, because I reached a point, and I might offer, if Nick gets questions while I'm drinking a bit, I could answer 1 or 2 questions around this, but I could also proceed with 2 more techniques. I indicated in which direction I'm heading. These 2 parts will then a little bit shorter. So I don't see or hear questions, then I continue and will talk about responses to small injections, to pulses. We have no breakthrough, but we have something at the inlet as a small perturbation, and we see responses. I come back to this figure later, and there is also a connection, of course, to the isotherm information. There are many people dealing with it. I picked a beautiful paper by Daniel Tongdeur from 1996. I have a graph from that paper on my next slide, but I want to remind you that Handan Tesel gave also in this early webinar series a nice introduction in this method of pulse chromatography, where she focused on binary adsorption data and brought interesting examples. I show here the figure of Daniel Tongdeur, where he drew the isotherm and he had local slopes at certain concentrations. And if you run a perturbation experiment on these local slopes, the response times of the perturbations will depend on the local slope, as you see here. This is the equation I also used in my introduction. Tongdeur brought a beautiful example of a 4-component system, so helium, nitrogen, methane, and butane, and he showed pulse responses for that system, which are very interesting. So there were 3 response times here. That was a system without a solvent which behaves inert, like in my case. I will come now to our examples, which originate again from the liquid phase, and want to first show you that this method is powerful, maybe a bit overlooked, because you can automate it also nicely. We did this many years ago in a PhD thesis by Clemens, and I also later did not use it too often. Here is the illustration of a single component pulse on a not preloaded column, so the initial state 0. If the state is reached, the equilibrium state for a new experiment, you inject here a pulse. In this case, it was a solvent, so a vacancy, a negative pulse, and you could measure then this retention time, and you could do it a couple of times. So by measuring these times, you record local slopes at the certain positions of your plateau. You can automate this experimentally if you have not much material, for example, you work in a closed loop starting from the highest concentration. You can fill, you equilibrate your fixed bed, then perturb from an outer loop by a small pulse of solvent. and then you bring a big pulse of solvents diluting in your loop. The scenario bringing the column back to the new state and giving a pulse again, which you detect. And Clemens did this, and here he has 4 pulses belonging to 4 of such loops. So obviously the highest concentration for Langmuirian system gives the shortest retention time, and the most dilute gives the longest retention time. So from these 4 times, which you clearly see and which you can extract without any detector calibration, and assuming now an isotherm model, which you need to derivatize. So you need to have the slope of the isotherm in theory, which depends then on parameters. You can easily estimate the parameters. And this is exemplified here now for a binary system. So we have here such a staircase experiment. Is the overshoot that you saw, that was the breakthrough analysis. We ignore this information now completely. We just look for the pulses, initially column empty, and then the pulses on the plateau. And you see, you have 2 pulses here, 2 components in an inert solvent trigger 2 waves. You can do the perturbation by pure solvent. This would be the 1, the 2 negative pulses. You can inject also 1 component alone, the other or both. If the perturbations are small enough, the retention times will always be the same, as Clemens has shown you here. The analysis, how to proceed, is here even written for an n-component system, where the core is that you have again to solve an nth order polynomial to identify these directional differentials which sit together with the partial derivative of your isotherm model in these total derivatives, which are directly proportional, linearly connected to the retention time that you measure. So if you understand the principles of the frontal analysis where we had the shocks, now we just have this local slope, a fixed point. And we can then use an objective function having the experimentally measured retention times and the theoretical ones, which required an isotherm model with parameters, unknown parameters, to estimate them. A beautiful example was done by Christian. This is even a complicated chiral separation on a chiral stationary phase. Not much details are given here, but the 2-phenoxy-2-propanol has 2 enantiomers. And here are plateau concentrations recorded for 14 plateaus. And always we have a first time and a second time. So pairwise they were recorded. The 1, are the analytical retention times on the empty column, so the biggest times, and then going up in concentration in 1 mixtures, we see always smaller times. We come then closer to the dead time of the system, so they match each other. So these times, in fact, 28 times were now plugged as experimental data in an objective function to be minimized, where the theory is using this isotherm model. So you have a competitive part with Langmuir and a non-competitive part with a third isotherm parameter. These are the lambdas. This is a model quite frequently used in the area of separating enantiomers. So we have 6 parameters, and here are the 6 parameters which have been relatively easy estimated from these 28 times. And of course, this equation can be easily derivatized to get these Jacobians or the partial derivatives as a function of these parameters. Let me come to the last part, the third part. What about intermediate injections? So no pulses, the small one, no big injection times, that the column is completely saturated with the feed state. In chromatography, we have very often intermediate situation, also because we have not always enough material to saturate totally the column. Then we can use a technique that analyzes the shape of the waves, the dispersive part. So we forget the shocks and we look at the shape of the waves. Now, this method is also quite old. In the 50s, already Glickauf worked on that. And in Gierschong's book, there is a longer chapter on the method called in this area the illusion by characteristic point method. Let me explain it to you a little bit based on an experimental chromatogram, which I, in the end, will use again. This was recently measured in our laboratory. I just show here that such shapes can be recorded, and that this equilibrium theory model that you saw before for infinite number of plates exactly describes such shapes. Here is a sum of the two components. Here you see the individual components. Always there's a shock of the first component, the dispersed wave, then comes the shock of the second component, and then there is a point where the first component is leaving the column, then the second component retards at the plateau, and we have this arc. So there are regions where the first component is alone, called here zone 1, and where the last component is alone. In this mixed region, the situation is more complicated. So this scenario is analyzed in the frame of the equilibrium theory. A couple of formulas are given. The notation we are using follows Gierschong's analytical solution, where we have this arc, the first arc, where the first component is alone, underlined in red, and where the last component is alone, underlined in red. So we can use this information quite easily using these formulas to get isotherm parameters back. They are again given here for the Langmuirian systems. The middle part, by the way, uses this R1. This is again a solution of a quadratic equation, but since I will not focus too much on this middle part, I will also not explain a few other symbols here. But the solution is well available and published a long time. With this, we can now play a little bit first parametrically. So if a chromatogram follows a very high efficiency, here simulated with 20,000 plates, these arcs are well visible and very pronounced. These are highlighted by these elliptic or circles in gray. If the efficiency drops, the arc shrinks that are available. So we can also take for one and the same experiment the whole arc up to the maximum, but we know at the maximum kinetic problems start to play a role. So it's wise to take not the whole arc. We sometimes talk about a whole range of information used or a narrow range, which is a little bit then empirically, I would say. But doing this, we can reconstruct with the analytical solution seen before these chromatograms quite well. The plate number, of course, is a big parameter here. If the plate number is just 625 compared to 5,000, we see a strong response on the shape and by this on the possibility to extract the information. So we think that about 2,000, 2,500 is sufficiently good to see these arcs well enough to take them as an input information in an objective function. So then the whole arc should be matched as good as possible. And here, based on theoretically predicted chromatograms with the dispersion model, where the original isotherm is provided, is known, we see how we can rematch them just by taking one chromatogram and these two arcs in an objective function. And the precision beyond 2000 is relatively well. The range of the isotherm arcs depends, of course, on the amount we inject, on the feed concentration. And so the higher the more we inject, the larger we can reach, or we can estimate the isotherm branches. This gives me the chance to come back to this experimental example that you saw before. I specify it again very briefly. It's for the separation of 2-phenylethanol and 3-phenylethanol. Again, a reverse system. And the chromatogram was recorded here with an UV detector at a certain wavelength. The method requires now a calibration because we need real concentrations to compare on the level of concentrations, the model and the theory. This detector calibration is not needed, for example, by the perturbation method mentioned before. So once we have done this, we can decide now where do we trust the branches. You see a little bit, there are also some impurity issues. Not only these two components are inside, at longer retention time something comes. So we are a bit careful. We have a narrower and a broader range, but both of them match relatively well the position of the chromatogram, then back calculated with the isotherm parameters. So this is a method which might in some cases be interesting, and we published it recently in Adsorption. So, and I want to conclude now this method also here with this short example. Let me summarize my webinar today. So I advertised a bit that dynamic experiments provide a lot of information regarding adsorption thermodynamics for the courses of adsorption isotherms, not only for single components, but also for mixtures. There are quite a few types of experiments available. I will not repeat them now in detail. I want to say that equilibrium theory is the guide to understand how these methods work, how they are interpreted, and also how the analysis needs to be done correctly, and we get a hint or help from equilibrium theory. I did not address today which isotherm models are used. I followed Langmuirian isotherms, using mostly the Langmuir isotherm itself, but there was also the modification with an additional linear term. Bi-Langmuir isotherms are often used in our area, but also the ideal or real adsorbed solution theories can be used, and isotherm parameters in these theories can be parametrized. I did not follow too much velocity changes. I addressed that. And for those of you that work in the gas phase, I highlighted the relevance of having information not only on the concentration courses, but on the outlet flow rates. I did not talk on temperatures. Everything was discussed isothermally. So to interpret such data, if there are temperature fluctuations, which are probably in the gas phase very often not easy to ignore, then additional energy balance considerations must be done. Regarding the methods, combinations can be used. I have just the 3 logos of my work here today. So I have these pulses, the initial pulses. They should be maybe always incorporated if available, because they reduce the number of additional free parameters. You can also include kinetic information explicitly. Then people sometimes call it the inverse method, fitting in more detail the responses, not only the first moment, the position, but also the shapes of that. This is interesting and is being done, but I think thermodynamics first. So the position of the front is the first that you should look at. The shape and the spreading comes after that. Here in the last slide, I show you a few references. Some of them I mentioned: equilibrium theory, the beautiful first paper of Ree, then Marcos and Arvind's review in the annual reviews of chemical and biomolecular engineering addresses equilibrium theory. Yeah, also in the chemical engineer's handbook is a lot. And we published a few years ago a paper which I extended today by new results in a way where we compared different methods. a major chapter on parameter estimation for thermodynamic. It's also in our third edition of the book, Preparative Chromatography, which just recently I put this here. Maybe not many will understand or read Russian language, but by any chance, it was translated into Russian recently. So, yeah, Nick and Giuseppe, with this, I would say I would like to close now and might stop share screening, or yeah, I will do that. I could share again and show my camera, and I'm ready to answer questions if there are any. So thanks for listening and for your attention.
Thank you. Thank you so much for such a enlightening presentation. In the meantime, we are waiting for questions coming from YouTube. I'd like to ask you some, if you don't mind.
Sure.
At the beginning of the presentation, we were speaking about how the shape of the isotherm were impacting on the breakthrough for adsorption and desorption shape. Could you elaborate on why the derivative in the equilibrium theory solution is approximated as a chord of the isotherm in a shock propagating, but it's as a derivative in a wave propagation? It was slide 7, if I recall correctly.
No, I was very short in that. Let me go again to my presentation. Maybe I have another. Yeah, I have a backup slide, which I did not comment too much, but on the top is this trajectory for a Langmuirian system at the column outlet, where we jump from an initial state 0 to a feed state. And the slope of the isotherm always decreases for Langmuirian systems if we increase the concentration. So I will not write here now, but that means that the speed of the front accelerates. So with other words, faster concentrations or points of higher concentration travel faster than points of lower concentration. And that would mean that they would surpass smaller concentrations. So at the outlet of the column, at first high concentrations should pop up before small concentrations have been there. And that's impossible. Huh? There are entropic reasons, and there is this sharpening of the front. Whereas in the desorption branch, the opposite takes place. Then the feed concentration is higher, and we jump to a lower concentration. And then this is possible and feasible that the fast concentrations travel faster than the slower ones. So this has to do with this issue. And if you look a bit in the equilibrium theory literature, the shock formation and the wave formation is a central point. I always explain it in our classes with this simple graph, a little bit better illustrated maybe. But fast traveling fronts of higher concentration cannot surpass the other ones. There is a condition that forces them to form a shock. And in the lower part, by the way, this is another backup I just have here in my slides. If you have a composite wave, then it depends on the feed point where there will be a shock, and you have some points. So the shock always tries to have the shortest connection from the feed point to the initial point, which is for an empty column, the 0 point. This is the so-called rubber band rule. You can try to have a rubber band between the feed state and the initial state, 0 in this case, and the adsorption branch is the rubber band connection below the isotherm, whereas the desorption branch follows above. And if there is a direct connection, then you have a shock. Otherwise, you have to follow the shape of the isotherm and you follow the slope. Just in brief, there is more to say, but I think gives you an idea and you can read this easily.
Thank you. Thank you so much for the explanation and the clarification. I'd like to go further, and in the slide afters, you spoke about the possibility of taking different equilibrium points from a breakthrough experiment involving different gas species. Based on your experience, what are the main challenges that the user may face while retrieving such equilibrium points?
You mean in gas phase experiments or in general?
Yes, gas phase.
Yeah, I think the paper that I cited by Nick and Arvind and Farouk shows also a lot of experimental issues that need to be treated with this. Again, the dead volume question must be addressed. It depends how precise you want to get the isotherm. In general, the method is not too difficult, and I would encourage people to use it more. The possibilities to detect nowadays, concentrations have improved. So with these Coriolis mass flow meters, you can detect flow perturbations. And so maybe in the gas phase, the temperature issue is a problem, that you have also to be very careful if there are temperature fluctuations. The liquid phase, in a way, is easier, not only due to the incompressibility of the fluid, but also due to the higher densities and heat capacities of the fluid phase. There are not too many such strong temperature fluctuations encountered. But read the paper of Nick. He presents many good lessons.
Yes, 100%. Staying on the liquid side instead, what issue could someone face if two peaks are overlapping? I mean, how different do the peaks need to apply the methods that you spoke about in the last slides?
You refer to the last method or in general, the selectivity questions? So the enantiomers that I mentioned are very similar, and they are difficult to separate. We have sometimes very low separation factors, say 1.1 or even less, and still you can resolve with these techniques the differences in their isotherms.
I was referring to selectivity.
Yeah. If you increase in concentration, so let me see, the perturbation experiment maybe is a good example to show you. Let me see if I can go back. So Christian's example so depending on the concentration in nonlinear systems, you can have information like the 2 times belonging to plateau 3 or 5, and the higher you go to the concentration, the closer they come. In the end, there is an end at T0. If the slopes become more or less 0, then you cannot rely too much more on the information. So I think the difference in these response times, in the retention times of breakthrough experiments is very much depending on the nonlinearity of the system combined with the concentration level at which you perform the experiment. Also, that means at the concentration level, you are interested in applying the isotherm later in your separation problem. These are the connections I want to mention here.
Thank you. Regarding instead the energy balance, at the last slide you mentioned that it was not taken into account, but could you elaborate a bit more how the absence of isothermal assumption can affect all the kind of adsorption experiment, gas, vapor, or liquid, with a focus on liquid I'd like to have.
So if you have no isothermal conditions, the isotherm depends on temperature. We know more or less the order of magnitude, but we don't know the isosteric heats of adsorption, for example, very often. So if within the column there are temperature changes, And in breakthrough experiments, temperature waves are traveling through the adsorber. They change then locally, dynamically the temperature. It means always there are different isotherms locally and temporarily driving the process that has an impact on the response time that you record at the outlet. So without solving together then the mass balances with the energy balance, you will not be able to have a very precise prediction. And for our problem today, you should be careful in solving the inverse problem, taking your observation at the outlet and calculating back isotherm parameters. So I think also in Farouk's paper, there are the energy balances given and there are more details on that. So this brings a new complexity, which is not easy to handle because you need new parameters for each component. But if you need precise description of your system, you need these parameters anyhow. And you might now do these experiments maybe at different temperature conditions and extract in addition parameters from the energy balances. This is also then inside, it's hidden inside the output information that you record. But the analysis is more complex. But I would say state of the art, and it could be done and should be done in many cases. I wanted to show today a little bit the general techniques available, and for relative quick estimations, the isotherms calculated in this way or estimated in this way are probably often good enough to provide key performance indicators of the process in an early stage. If you look then in this non-isothermal issue, you need to invest more.
Thank you. Thank you so much for such clarification. I think it's all for the questions today, and I'd like to give the floor back to Nick.
Yeah, thank you. Then I stop share screening, and I might stop my video as well.
Thank you, Dr. Andreas Seidel-Morgenstern, for your presentation, Dynamic Methods to Measure Competitive Adsorption Isotherms. We also thank all of our attendees for joining this webinar and hope that it was both educational and enjoyable. An edited version of this webinar will be posted on the IAS YouTube channel and Bilibili with an announcement on the IAS Twitter feed. The hope is that the work discussed here today will be a useful resource for the adsorption science community in the future. The next confirmed IAS webinar will be given by Dr. Matteo Gazzani on July 11th at 1400 UTC. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed and through the IAS mailing list. With that, we thank you for joining us and hope that you will join us again soon.